Okay, it started recording. So, welcome to week 6 optimization from fundamentals. So, before we begin, any doubts on the material that has been covered?
Yeah, I have a doubt regarding the proof
Yes.
of equivalence. So
Yes.
if I take note this down, just give me a second.
Yeah,
I'll
yeah, sure.
pull it out. Just a second. Just a second.
Yeah.
Yeah, this is. I do not know how I shall present it because this was during the proof of this theorem,
The strong duality
the
theorem.
the, the equivalence of BFS and extreme points of P.
Okay, right.
Okay, so at
Yeah.
one time, while he was considering part two consists of the case when x is a vector,
Hmm.
the first m components are non-zero and the less, and then the next n minus n m components are zero.
Right.
Okay,
Right.
so he was proving at some point
Hmm.
that we can choose. He was first considering y hat, where which consists of first k values of w1 to wk, and the rest n minus k w's are zero. Okay, then he says that we can choose epsilon small enough so that x plus epsilon w hat greater than equal to 0 and x minus epsilon w hat greater than equal. This how he was considering these things, I'm not understanding actually.
So, okay, so just a second. So, this is about equivalence of PFS and extreme points, right?
Yeah,
Okay, so you are saying, let's say that x is an extreme point.
means I can also dictate the previous parts of the proof to give you context so that it will be easy for you to write it down, the
No, it's
particular
fine. I
statements.
mean, I have my notes here, so
Okay, okay.
I'll just directly jump into to this question. So this is the second part of the proof where we are assuming that this x is an extreme point, and we are trying to show that this will imply that x is a basic feasible solution as well.
Yes, yes,
Okay,
yes.
so here because it's a feasible point, so x belongs to P, right? So x is greater than equal to 0,
Yeah.
right? And what else can I say? So and then you have a corresponding. So maybe let me write both x and w. So x and there is w hat. These are also k and the first k entries. Okay, so you are saying, okay, now we take x plus epsilon w hat and x minus epsilon w hat such that, right. So what is the doubt here in this part?
Means how means are you always assured that we can select such a epsilon in this case? Means that is what my I'm not clear about. Maybe I'm missing something.
Right. So what you can do is you can just look at. So here the w hat is of our interest, right?
Yeah.
So what we'll do is we'll just look at the maximum. Uh, yeah, you'll be looking at the, sorry, not maximum. So you look at the smallest. Oh no, sorry. What am I doing? Uh, Yeah, you can say largest negative value and smallest positive value in these k components. In these key components. So
Okay.
then based on that I can choose that epsilon, right?
Okay, the largest negative value and the smallest positive
Yeah,
value.
so it's like I want to subtract from these components. So okay, by the way, here this will also have to take into account what are the largest and the smallest values of x, right?
Yeah,
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 so
that's true.
so that we just keep track of these four things so that we can find the appropriate epsilon.
Okay. So we do not need to invoke any concepts of open and closed sets
No,
for
no,
this,
no,
right? I
no.
was
So here we have only finitely many entries, right? Here you have k entries x1 to xk, and here you have the first k entries of w hat. So we just get an idea of okay, what is the range of x, what are the smallest and the largest values. Same for the w hat, and accordingly a w hat, and then accordingly choose the epsilon. We just want to nudge the entries of x slightly such that they still remain non-negative. It's
Yeah,
all
it's
only
like a perturbative proof, right? It
yes, yeah,
perturbs the entries, right?
yeah, just perturbations, yeah.
Yeah. So that's okay. That's fine. I got the idea. Yes.
So the advantage of doing is that you perturbed and you saw that okay, the midpoint of these two is actually turning out to be a sorry, x can be written as an average of these 2 points, feasible points, and that of course contradicts the fact that x is an
And
extreme
not an
point.
extreme point. Yeah. That's okay. The next part is okay. I was just wondering how we came up was
Right,
without it.
right. Oh, I hope
So
this is
that's
clear now.
yeah. Then it is everything is clear. Then
Okay,
everything is clear.
let me just
And
quickly
another thing I wanted to ask is,
yeah.
means I haven't got to the week 7 videos. So are the applications of duality very extensive in linear programming? I was just wondering.
Yes. So not just linear programming. I mean, in general, a lot of times if you try to cast a problem, primal into dual form, it might turn out to be simpler formulation. So you might end up even in machine learning, you might see that when you look at the dual problem, you might see that okay, perhaps this is an easier way to solve it.
Yeah, probably the support vector machines case, right?
Yeah, yeah. I mean, I'm just trying to say that it's not just the case with linear programming. Even in general, if you have let's say just more broadly speaking, convex programming situations, you can still perhaps recast the problem as a dual problem and then perhaps solve that problem alternatively.
So the duality thing is an overarching theme, right? Everywhere it runs
Yes.
through the entire thread of machine learning, right? I mean, sorry, optimization theory,
Yeah,
right?
yeah, yeah. It's a really important part. Yeah.
It will be coming on again and again in later weeks, right? In some form or the other.
Yeah, yeah, it will and you will see as he very briefly alluded to, this relation is essentially you will look at these KKT conditions. So the Lagrangian multipliers that you will see that they will be capturing this duality relationship.
Okay,
Yeah,
got
it
it.
will all come
Yeah.
be unified in the
So
coming weeks.
okay, so this is just easing into duality, right? In the context of linear programming, right?
Yeah, so for example, I mean just to maybe say a bit more, if you recall in the proof of strong duality, so this is the week 6 only, not week 7.
Yeah,
Week
that I
6.
go, that I know.
Yeah, right. So this proof of strong duality, we constructed a set which was
Yes, R omega set, right?
projection of a polyhedron that we defined as. So he briefly alludes to this. I am just reiterating that this here. So what we are doing really is corresponding to my constraints. So maybe let me just write it down first. So corresponding to constraints, so in my okay, so maybe I should write this ax equals to b and x greater than equal to 0 is my constraint set, right? So this A is a m cross n matrix, m being the number of rows. So that means there are m constraints. Corresponding to those each constraints, I get a quantity. And of course, I have my decision variables, my variables for which I'm optimizing the x. So with them, if I have to construct some appropriate set, and through that I can prove such results. So this is just points out that the way to think about formulating these problems would be to understand the relationship between not so surprisingly the variables x and the constraints. So how to express that? So you will soon see that this all can be ultimately you can formulate these conditions that are called KKT conditions, and that will perhaps give more insights into what's really going
Yeah,
on
he
here.
just briefly that you have just told.
Yeah.
That it captures the tension somehow between the decision variables and the constraints. This
Yeah.
entire set S.
Yeah. Of course, we
Okay.
have not talked about how to construct these sets. So let's see.
Yeah.
I'm not sure if he'll discuss in the coming weeks, but I think probably he will.
Yeah,
So we'll see.
but he mentions in the passing that these sets can be constructed means based on general considerations. He
Yeah.
just said that.
Yeah.
So I think there is some general recipe, but by which we can come up with such sets. But he didn't mention that, right?
Yeah, I mean, I personally, I don't know if we can in general come up with such sets. Uh, I don't know. Let's say linear programming, maybe it was a bit clear, but not sure if in general if I have a convex programming problem, if I can do it or not. I'm not sure. I have to think about it. I have not seen such proof, so maybe
Okay.
in the coming lectures, if it comes in the lectures, we can take it up and.
No, but my doubt was that but how he went through the proof by constructing S, it looks a bit concocted. Means that was I was wondering how he came up with such schemes.
Yeah. I mean, even I right now don't have any intuition to give.
Yeah, means I was kind of quite a long time brooding over how he came over these definitions. That's what it was kind of bit opaque to me at this point.
Yeah.
Anyways, we'll see.
Yeah, I mean, he probably even separating hyperplane theorem should have been covered, but it's okay. We'll just take a look at some problems and see what.
You told that you would go over some problems regarding multivariable calculus and such to clarify some of the issues. You just told yes, previous class.
Multivariable. I mean, what I could do is I could solve some problems where you would just get used to computing the derivatives, where you have multivariate functions. That's the thought I have. So, is it okay? Shall we go ahead with that?
Yeah. Whatever help it will be helpful for me to just
Because
get
I
a
feel
rehash
like
over
in the beginning there was this discussion about the first order, second order necessary conditions, but unfortunately there were not many problems. There was only one nice problem in the problem sheets. I forget which week it was, but other than that, it's pretty much straightforward. So let's just start with a few calculations. Initially, it might seem a bit complicated, but let's just try it out. So I'm deviating a bit here. I'll come back to this week's assignment questions after some time. I hope that's fine.
Yeah.
Some warm-up questions. So we'll just start with something simpler. We'll take a 2D function, and so x is a vector with the components x1, x2. So what are the minimizers of f of x? How will you find them?
So these are unconstrained optimization problem, right?
Yes. So yeah, you are right. So first I should write this. This is very important. Whatever it is, f of x and x1, x2 both belong to R. So what do we do first? It's an unconstrained optimization problem. So what do we do? for unconstrained cases.
So we start with the derivatives, right?
Right, but here it's a multivariate function, right? It's not a one. The variable, there are two variables, not just one variable.
Okay. I need a bit of jogging, means I forgot all of those things.
Okay, so when we do this, what we should really start off by saying is, okay, the necessary condition. So let's say there is a point called x star. Let's say it's a minimizer. Okay, it's our candidate point. We want to find what are the values for this candidate minimizer. Okay, but for it to be a minimizer, it has to satisfy some necessary conditions, right? So we saw that this is an unconstrained optimization, meaning this is an open set. So if I'm optimizing in an open set, then the gradient of this has to be 0.
Yeah, correct. The gradient.
Okay, so this is first order necessary condition. I'll just write in short as FONC. Okay. So I'm just writing what I said. So I compute the gradient, I equate it to 0 at this point. So what is the gradient at this point? Let's see. So we can simply write 4x1 minus x2 cube. So just this part has x1, this part has x1, this part has x1. These three terms are of no relevance to us when we are differentiating with respect to x1. We're just taking partial derivatives. I hope that this part is fine.
Yeah, that is fine.
Okay, so I can similarly write the partial derivative here with respect.
So this will have, this derivative matrix will have one column, right? Because on the single variable.
Yeah, it's a gradient will be a vector. Yes, because it need not be. It could be a Jacobian, but here it's a scalar valued function. If it was R2 to R2, then it will be a matrix.
It will have two columns, one for each function, right?
Yeah.
One component of that function.
Yeah. Minus 2x2. Okay, yeah, correct. So what will this give us essentially? This will give us can add. Okay, so you'll get x1 star equals to x2 star.
Yeah, x1 star, and that is a.
I can just add the two and I can get this. Okay.
Yeah.
So if you put this here again, what you will end up getting is so for example, this whole quantity you can keep here equal to 0. So when I say 0, I was being a bit lazy here, so I meant 0, 0. Vector. So when we put this fact that x1 star is x2 star, we'll put that here because this is still satisfied. So ultimately what we'll get is both are 1 because 2x1 star minus x2 is 0.
Okay.
So 2x1 star minus 2 is 0. This implies x1 star equals to 1 equals to x2 star. So our candidate point is x1 star, x2 star is 1. Right?
Yeah. But after that, we'll have to go for the sufficient conditions, right?
No, not sufficient. So we still just check the first order condition. We'll check the second order condition now. So what we have done here is we have set our candidate point. So here we had two unknowns, we had two equations. So we solved that and we found that x star is 1, 1. But it is just a necessary condition. So
yeah.
So what you are saying, if it's a sufficiency, then great. Then we can say something. Otherwise, we can't say. So what we'll do is we'll just compute the Hessian.
But I was thinking that since we have one candidate solutions, can we just not go about checking the Hessian? It's not true, right? You'll have to check the Hessian always, right?
So if I have to check the Hessian because I only satisfy the first order necessary condition.
Okay.
Right, I'm in an open set. I satisfy the FONC. Okay. Now I have to look at the second order condition. So let's just see what it looks like. So what will be the Hessian? So okay, I unknowingly thought I had a laser pointer. Extremely sorry.
It's being recorded, right? Otherwise.
Yeah, I think it's. Let me still confirm. I hope it's still recorded. Yeah, it's recording. Yeah, no, I thought that it was a
So
laser
crazy
pointer,
mistake.
but okay, sorry about that. Yeah, so we can just again, it's a simple calculation. So we again take partial derivatives of the gradient that we saw, gradient vector. So what we'll end up getting is, so what I've done here is nothing special. So this entire vector, I have to take partial derivatives of this with respect to x1 and x2 separately, right? So this quantity, I take the derivative with respect to x1 and x2, right? So correspondingly, I get 12 times x1 minus x2 square plus 2. And similarly, if I take with respect to just x2, and what I'll get is just 12 times x1 minus x2 cube, with a minus sign. And same thing for the second quantity. So I've just written that here. And we'll want to evaluate this at x star equals to 1, 1. Okay. And
So
it is
at 1,
2, 0,
always
0 minus 2.
0 minus 2.
Okay, but so the thing is, this is not positive definite, because that is what our second order sufficient condition is, right?
Okay.
So unfortunately there was only one candidate point, which was 1, 1, and that doesn't satisfy our second order sufficient condition, not even necessary condition. Okay,
Yeah.
so no minimizer for this, no unconstrained minimizer.
Yeah, but constraint the situation may totally change.
Yeah,
right?
constraint may change, but here you see the problem, right? It's for the simple reason that you have these linear terms, these terms.
Yeah, true.
So
That are unbounded, right?
yeah, this will be non-negative, but then I can always control this term.
Okay.
For this, I mean, to put it simply, I can first of all keep okay, x1 equals to x2. If I keep that's first of all the not going to help me, but in general, because these linear terms present, I can actually make it unbounded.
No, so is it possible in a general cases to just eyeball into some forms of effects and tell whether a minimizer exists or not?
No,
It's
no,
not possible.
it's not a good strategy, because multivariate
Yeah.
functions you can't keep track. How, I mean, here it was just polynomials, but you can have some very complicated terms also, sines, cosines,
Okay.
and all other logarithms, exponentials. So
Okay.
yeah, eyeballing won't be a good strategy. You just focus on checking whether the necessary conditions, first order and second order necessary conditions, are satisfied. If they are done, then we will take the next step and see whether sufficiency is also satisfied or not. Okay. All right. So now I am saying there are. So this is our favorite setting, linear regression. So what we are saying is there is a best fit. Okay. So
That I did not understand the notation for I. For all I belongs to natural numbers, right?
not natural number. I mean, some n data points are there. I just wrote it
Okay.
in a
N is
shorthand.
an index. Okay.
Yeah. I just meant to say there are n data points. Xi is the input, and yi is the output. It's a linear relationship. So y equals to ax plus b. You have to find the optimal a and b. I am denoting those optimal points by a star, b star. So in general, if I write an optimal point, I'll denote it by star, superscript star. Okay, so a star, b star, they are the minimizers, so they are the arcmin of the following: xi plus p minus yi whole square. I take the residues. I have a model ax plus b. I give input xi. I give input xi to my model ax plus b. Out comes some yi hat. I check what is the prediction error, yi hat minus yi. I call this residue or error, whichever term you're comfortable with. I take a square of each of these errors or residues and just take an average. Basically, this is an average square error. So I want to minimize that error, and whichever a and b that give me this minimum average squared error, those are my best line fit parameters. Okay. And just to just to make things a bit easy, we will adopt
I have a small question. So if we want to incorporate some prior information into A star B star, then it will be a constant optimization, right?
Yes, correct. You're right.
Okay.
So right now because I did not mention anything here, AB, I just wrote AB here, so we will assume that it's an unconstrained optimization problem for me. And I'm just writing a few things. So I'm saying that x bar is the average of the xi points. Similarly, I can define x. So these are just notations that I'm defining. Similarly, x bar square, defining average of the squares of the samples. Okay. And similarly, I can define average of xy, so that we can maybe write it a bit compactly. Okay, and y bar is again average of yi, and similarly y square bar, so average of the yi squares. So I'm just defining this notation for our convenience. So far so good. This is what we are given. So we want to find this A star B star. Okay.
Yeah.
So first thing that we'll do is, maybe what we will do is call this whole function, the whole function, as some f of AB. Okay, so what I'm saying is, just to keep it less cluttered, A star B star is the variables that minimize our function f of AB, and f of AB is the least square error, right? Least square error that we have written here, the average of all these squares of errors.
Yeah.
Okay, so how do we do this? Any thoughts?
I think we, again, since it's an unconstrained optimization, we go for the gradient only, right? Gradient vector.
Yeah, so we'll do that, but first we'll simplify a bit. So what I'm saying is, it will be nice if I can write this f of AB as some form like this. So Z is AB, Q is some matrix, C is some vector, and D is some scalar. So if we can express it in some forms of just matrix vector products, it will be much easier to compute the gradients.
So yeah, because we have the standard prescriptions, right, for these kind of forms, right?
Yeah, I mean, so even other than that, even if you want to solve analytically, it will help if you can express your function into such forms. It just makes it very easy for you to comment on the Just do the gradient computation. Otherwise, you'll have to take for each coordinate. You'll have to write. So there will be a lot of indices that you'll have to write.
Okay.
That's all. So question is find Q, C, and D. Okay. So what do? We'll just start writing what f of a comma b is. So as we said earlier, we have written f of ab as summation axi plus b minus yi whole squared, taking an average of this square errors. So what we'll do, we'll again just keep on expanding the sum and simplify. So axi squared plus b squared plus 2axib.
So without expanding, it's not possible, right? No.
Yeah, I mean here you'll have, otherwise you might miss out some terms. So a hint is that there will be terms of this kind.
Yeah.
So that's why I just defined it here
Mm-hmm.
for our convenience. So I'm just expanding this square term. Okay, and so notice that this is summation goes, these are linear terms, summation goes inside summation xi squared by n, that we defined it to be x bar square, right? Let me write it clearly. A square x square bar, well, b square remains b square because 1 by n summation constant 1, that is b squared plus 2ab. Here you have summation xi, summation over 1 by n, so you have x bar, and by the same logic we get summation yi square by n. So here also you will get a y bar square. I'm just redefining the terms, that's all. I'm not writing, I'm not changing, I'm not doing any manipulations, just notifying it by some compact notation. And if you keep doing that, you will ultimately get this. So what does this give us? See, remember, what I want to do is I want to express this function f of ab as some matrix vector products where the vector happens to be of this form. The vector is basically the variables over which I'm optimizing, the a and b. So I already have my a's and b's, and they are occurring in a quadratic form. So it's not surprising to see that it will turn out to be a form like this. Okay, so even if I did not tell you that f of ab should look like this, just the fact that you expanded this term for all the samples, just take an average and you rewrite the terms, you will start to see that there is some quadratic form that's going on, and we can compactly represent this quadratic form. So for example, what you can do is this. You can write, so we'll start somewhat simpler. So what we'll do is we will first write for this term. So I'm just writing it as some vector transpose some other vector. Here also I've done the same thing. Is it fine so far?
Yeah, it's fine.
I've just rewritten this term. So this whole thing comes as a inner product of two vectors. Leave this scalar alone. And this thing can again be expressed as a inner product with two vectors, where one of the vectors happens to be this AB vector. That's what we are interested. Now you can also decompose this into a matrix vector form. So what we'll end up getting is the following. So with this A and B basically will come here. You just remove the A's and B's. So it's clear, right? So what we'll end up doing is AB x bar square x bar 1 AB plus 2 minus xy bar minus y bar AB plus y bar square, or the y square bar. Is it y bar square or y square bar? It's y square bar. Y square bar. Okay. So this is my Z transpose. This is my Q. This is my Z. And what did I write? 2C transpose. Okay. So then this is my C transpose. This is my Z, and this is my D. Okay. So now that we have done this, so maybe let me call this A. Let me call this part A. Part B is find the A star and B star. So what I'm saying is you minimize A, B, Z transpose QZ plus 2C transpose Z plus D. So how do we do this?
Yeah, so we take the this vector from whatever knowledge you have of vector calculus, take the calculated derivatives directly, right?
Yeah, so we'll just take the derivative. Now here it's simpler, right? Here I have compactly written, so it's very simple here. So what it will turn out to be for this quantity,
this will be 2 Z transpose Q.
Yeah, it will be simply 2Z. So okay, maybe let me not skip that step. So if you can just try this out. So what this will turn out to be is Q plus Q transpose Z. But here Q is symmetric. These diagonal entries are the same. So it will turn out to be Q is same as Q transpose. So I'm just writing that here. So that will be 2QZ plus this quantity, the derivative is simply 2C, right? Because it's just a linear term.
Yeah, 2C.
And of course this is a constant, so the gradient of this quantity with respect to Z is 0. So and here let's just assume that this Q is invertible. Okay, the data is given such that the Q is invertible. So our Z star is nothing but Q inverse C. Right, this is our A star and B star. And it can be more precise. So let's try to find the form for the A star and B star. So again, like I said, let's assume that the data is such that Q happens to be invertible. So because it's a 2 cross 2 matrix, that just corresponds.
But don't we have to check for this thing, the second order conditions?
Yeah. So we didn't say that it is a. So okay. So maybe I should have been a bit careful. Let me not. Okay, he has not covered convex function. So here it's a convex function, so it will happen to be the minimizer. We'll show that. We'll do that calculation very, very shortly. But let's just go ahead for now. Just take my word that this is actually satisfying the second order conditions as well. Let's just compute the inverse Okay.
Okay.
So Q inverse, I mean here, like I was saying, it's a 2 cross 2 matrix. So it ends up that you flip these entries and you put a negative sign on the diagonal entries. So what we end up getting is square bar minus x bar square, this thing, times 1 minus x bar minus x bar x square bar, and c happens to be this minus xy bar minus y bar. So if you simplify this, what you will end up getting is I mean if you substitute this q inverse, if you substitute it here, so I think I probably unknowingly multiplied it here. That was not my intention. So this is q inverse. Let me erase this. I'll just mention that this c is this. That's what I meant to say. So if we do this, where we put this computed inverse of q back, so z star, which is a star b star, it will turn out to be, let's see what the function is. Okay, so if we do this algebra, what it will turn out to be is xy whole bar minus x bar y square bar by x square bar whole square. So I think this is just common, I can take it out. This exact algebra is not important, but just writing here for completion.
Yeah, this last part is a little bit messy.
So what I have done is I want to take an inverse of this term. Okay, so what's the determinant of this? X square bar minus x bar whole
X square
square,
minus
right?
x bar whole square. Yeah, that one. Yeah.
Okay, so similarly, in the 2 cross 2 case, the inverse simply happens to be this scaling by determinant times a matrix where you flip the sign, right? Because that's how you
Yeah,
get the cofactors.
yeah.
So I've just done that. I've put this q inverse here. So I've computed my z star as q inverse times c, and c is this vector. Okay. So I'm just putting that. I just skipped that calculation because it's not like it's going to tell anything particularly interesting at this point. But we will need this because you like you asked, I need to check the second order condition, so we will need it for that.
Yeah, for linear regression, we know it will be a minimum always. But anyways, for sanity.
Yeah, I mean we'll just continue to check by first principles and see whether indeed it is what we are expecting. Okay, so yeah, I think I didn't write a bit properly here, but let me just remove this completely. It's very confusing. So these are my A star and B star. And by the way, if I take the Hessian of this whole function, what will be the Hessian?
Yeah, it will just be 2q, right?
Yeah.
So that proves it. Yeah.
So here says 2q, right? And that's nothing but saying x square bar x bar 1. Okay. And so for this meaning, okay, let me write for this Hessian. So let me call this H for Hessian to be positive definite. we want the upper left minus the determinant of these minus to be 0, greater than 0. So determinant of this constant quantity is what? It's the constant itself, and this is obviously greater than 0.
Yeah.
Right, so when I say upper minimum, I mean this whole thing, then this whole thing. If you 3 cross 3, it will go on. So this is the
Yeah.
Sylvester criterion.
Yeah, Sylvester criteria.
So, and similarly for the whole matrix, it will be x square minus x bar square. This is the variance of x, roughly speaking.
That is also greater than 0.
Right, so H is PD for all Z in R2. Okay. So A star B star is a global minimizer. Is it fine?
Yeah, perfect.
And if you just plug this A star and B star, and you give the average sample, average of all the points, you can just check that this will be y bar.
Okay.
Yeah, just a sanity check that it's a linear function. You would expect if you give
Okay.
average input, then you should spit out average output.
Okay. It's anyways a linear function. It is evident. Yeah.
Yeah. Okay. All right. So I'm just saying specifically for A star B star, not for any A B. But if you put that A star B star, the way we found the expressions, still then it will get the same.
Okay.
Yeah, let's do.
I want a suggestion from you. Can you suggest some text or reference notes, whatever I can do to jog my memory of multivariable calculus in the context of optimization? I am going to the Chong book. Chong book has quite a good deal of stuff, but
Yeah.
any other suggestions you have for
No,
going
that
through?
is more than enough actually.
More than enough, right?
Yeah.
Fine.
Yeah. Tongin's will be more than enough. So this was question 2 or 1? Question 2. Okay.
It was question 2.
So let's try one more fitting problem. This was line fitting. This is polynomial fitting now. Okay. So what we are doing is we are approximating function g over the interval 0 1 by polynomial p of degree n. So you might have seen a theorem like this in analysis, but we'll just try to do it numerically. Okay, so what the way to formulate would be, here in this case, one way to do it would be gx minus, so okay, approximate what? Approximate g. Approximate by what? By a polynomial p. Over what? Over interval 0 1. What's the degree of the polynomial? N. So based on that, so if you notice, all I've done is same thing. I'm still summing over my samples.
Yeah.
Okay, I'm just taking an average here also. An average here, because its length is 1, the denominator is also 1. So I'm still doing the same thing, but because continuous space, so this is what I'm writing. Okay, so I have to minimize this, and of course px is 0 to n ai x to the I. Okay, so what do we do? What do we find? So what are the variables?
So variables are all the coefficients of the polynomials, right?
Right. So a0 to a n, yeah, a n f of a1 blah 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 a0 up to a n, right?
Yeah.
So okay, so this is fine. Let me create some space. So let me rewrite this, let me expand this, given that px is some polynomial. So gfx minus a0 a1x minus an x to the n whole squared dx. So what do we do now?
Yeah. Now I'm thinking what we should expand to do
So
something.
what do we want to do here still? What is the
Uh,
objective of this problem? Have to
we again
minimize
have to minimize,
a
minimize.
f of a, right?
Yeah.
And a is over.
A is over. Wait. A is over. Yeah. A is also over reals, right?
It's a vector, right? So it's n plus 1, rn plus 1. It's an
Yeah.
unconstrained
It's vector
optimization.
Rn. Yeah. Rn plus one. Unconstrained optimization. Yeah.
Okay, so we do the same thing that we have been doing so far. So what we'll
So
do
now we
is,
have to take
yeah,
differentiation under integral sign, right?
yeah. So for now, we'll just assume that those complications don't arise. We can just take the differentiation inside the integral sign. We'll
Okay.
just keep it simple for now. So what we'll do is we'll take the derivative of this with respect to each of these ai's, and just look at that gradient, and maybe some pattern will emerge out of it.
Okay. Okay.
So I have to take the gradient of this. I can assume that the gradient can be switched with the integral sign. Okay. So what will this turn out to be?
There will be n plus one terms, right? In the
Yeah. So there will be the vector will be n cross n plus 1,
yeah.
n plus 1 cross 1, and we are taking the different derivative of this with respect to some ai. So the square will go, this term will come here, and then there will be some multiplicative factor. So let me just write it down. Okay, so what we want is really the FONC. I mean, we want to check this, what is or what AI satisfy this FONC condition. So that FONC condition, what does it say? Del f of a, del AI is 0 for I equals to 0, 1, n, right? Okay. So what can we say? So we have this whole thing equal to 0. So what can we say?
So all the integrals must vanish, right?
Yeah, so what we can say is just
Yeah.
rewriting
For
it again
yeah.
algebraically.
Yeah.
Just taking some terms on the right side. So what I am getting is 0 to n aj xj xi dx, and this is nothing but summation j 0 to n aj integral 0 to 1 x, there will be a minus sign here, x j plus I dx. So this whole thing is what? I can just write x to the j plus I plus 1 by j plus I plus 1, 0 to 1, right?
Yeah.
And that is nothing but I plus j plus 1 over I plus j plus 1.
Okay.
So so what I'll end up getting is 0 to 1 gx x to the I, minus sign, minus x to the I dx equal to 0 to n aj 1 by j plus I plus 1. So what have we shown? What we have shown is this quantity, this integral, is equal to the inner product of the vector A with this vector containing quantities like this. So I'll just write it compactly like this. Okay, I think you can do one more simplification, maybe can get rid of the negative sign so that it's not to worry about that anymore. So I'm just writing this for different values of j in this compact vector form. Is it fine?
Yeah.
Okay. So but note that this was for each I, right? For each I which is 0 ranging from 0 to n.
Yeah, for each component, right, of the gradient.
Yeah. So what we'll ultimately end up getting is something like this. I'm just writing the components corresponding to each I. If you have any doubt, just please let me know, okay? If I'm going fast or slow, just let me know. So I just wrote for each I, okay, the left hand side, I just wrote for each I and just stacked them. These are all scalars, right? I just stacked them into a vector.
Yeah.
And I'm going to do the same thing here. Okay, so see, this is a scalar, right? Some vector transpose some vector. So I can also write a transpose of this, meaning I can make this as a row vector and this as a column vector, right? I can just write this, let's say this is x and this is y. Then x transpose y same as y transpose x, right?
Yeah.
So what I'll do is I'll just stack these as rows of a matrix and let this be a vector. And I'll just put that here. So what I'm trying to say is, what I'll do is 1 by 2. Okay, let me maybe rewrite it like this so that there's no confusion whatsoever. So what I'm trying to say is, I have written it like this. It's a row vector. Is it fine now?
Yeah.
So
but how is it going to help?
Yeah. So I will first. So let's just write it down and see what happens. So I will stack this as my rows here for each I. Okay, and this vector of course stays as it is here. So let's just write it down and see how it looks like.
Yeah, this matrix looks very familiar. It has a name, I think.
Yeah, we will simplify it. Just hold on. So A0 AN. Okay, so I hope that this algebra is so far making sense.
Yeah, it's clear.
Okay, but we just have to unfortunately leave it at that right now.
Okay.
It's a bit tricky to say. But the point is just for you to get familiarized a bit with this calculus.
Okay. So this gives a flavor of Fourier approximation also. That is also some approximation of by periodic
Uh,
functions.
Are you referring to circular matrix? This is not a circular matrix, by the way.
This is not a circular matrix. No, no, there is another called Vandermonde matrix. I don't know whether this is that.
No. This is not that. No,
This is not that, right?
no.
Okay, okay.
Yeah. So, just want to show that lot of times, it's a bit important the way we formulate it when we are writing on a piece of paper. If we just write down for each term, it quickly gets out of hand. So these vector and matrix form. I mean, if we compactly write it using vectors and matrices, it just comes in really handy. And of course, ultimately, we want a computer to solve these. So that's another reason for why we do it this way. But even when you're deriving by hand, you see, right, how complicated the expressions are becoming.
Yeah, means actually in one shot you get rid of all the indices in one compact notation. That's
Yeah,
very handy.
yeah. So if I want to find that, if I want to find my a naught to a n. So this, by the way, is my a star.
These matrices will always be invertible, right? Yeah, by the characterization, by the construction, they are invertible, right? Yeah.
So the matrix for invertibility here, you'll have to. There's one way to check it. For example, here each and every element. So this matrix, if it is diagonally dominant, it will be invertible.
Okay, 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 yeah.
But here it's not. I mean, it's not a. Something like that won't help you. It's just a sufficient condition.
Okay.
So it's a bit hard to say just by looking at it. How will you?
Okay, okay. Mm.
So here, because in this case at least, it looks like one is more than the summation here. But then here clearly it's not true. 1/3 is not greater than 1.
Yeah, it's not.
So there are many. So it should be the case that for each row, if you look at the diagonal, it's
The
greater than
highest
the
element,
remaining
that is the
entries,
highest.
and then
Yeah,
that will be a sufficient condition. But then that check is not helping here. So maybe there are
yeah,
maybe you can other ways to clever ways to check it for high
yeah.
large n's, where we cannot
Mm.
write down and literally write down and check
Yeah,
by
yeah.
hand. Okay, so maybe we'll do a few more before we go to the assignment questions from week 6. Yeah, there are a few more two nice ones. Let's see how many we can do. Again, we are doing some fitting. So again, we are in a regression setting. So what we are given is samples of a function.
I was just wondering if we want to do a quadratic fitting instead of a linear.
Yes. Hello.
Yeah. Hello.
Yeah.
Okay.
Yeah. You were saying?
No, I was saying that if we want to do a quadratic fitting, a same kind of formulation will occur, right? As in
So
the
I
linear
think one
case.
way to do it would be in this case. What you can do is you can keep your gx as your y, right? Sorry, not y. What am I saying? G of x.
No, I was referring to the linear fitting which we did in the second problem.
Okay.
If we want to do in the quadratic setting.
Right. Yeah. So that's what I was partly coming at. So you'll have to basically in this case, since I've already written it here, can just imagine that there is an average here. You forget the integral sign.
Okay.
So instead of g of x, you put your yi for each sample. And p of x, let's just pick the degree to be 2.
Okay.
So it will vastly simplify. For example, your gx will be a constant here, right? Just the y.
Yeah, gx.
So gx comes out, you just have to you just take an average over the summation yi xi. So
yeah.
By the way, that's exactly what we got here. If you notice, Where is it? I think there's some place where we evaluated f of z, right?
I think
Okay.
this is yeah, this is the one you simplified, right?
Yeah, but I was just trying to show some term. Let me see. Um, I have to check the derivatives. Q inverse. Okay. Set. Oh yeah, this is what I'm saying. The C. So you take the Q on this side. So what you are getting is C. That C is basically like our term this vector. Why is that? See this average of product of xy or just y.
Okay, yeah.
See here you just take an average over y. Here you take an average over xy.
Okay.
Okay, so I just yeah, that's what I was trying to look for.
Okay.
So here that makes sense because we took n equals to 1, but if you take n equals to 2, you'll get summation yx squared via xi squared
Yeah, yx
average,
square, yeah.
and
Yeah.
similarly here you'll get a 2 cross 2 matrix. Oh sorry, 3 cross 3
3 cross
matrix.
3, yeah,
Yeah.
3 cross 3 matrix, yeah.
So I'm just, so this is also somewhat general case where you can just restrict n to 2 and can you see that
Okay.
this analysis helps you generalize it for such cases also.
Okay.
So we will again try some fitting problem. Okay, and so we are given samples of G and they are functions of some variable s, and there are s, so there are I such samples, sorry, n such samples. I is the index, there are n such samples, so we are given capital N samples of g of x function, and the locations, the x at which we have the value, these are, we are calling it SI, and we are approximating this function with again a polynomial just like we saw. Okay. So what we'll do is we'll ask slightly related to what you are asking. You earlier you were asking, right, what if I put priors on my A's, my optimizing variables, so how will
Yeah,
the, right, so we'll
yeah.
just do a toy version of such a problem. So where we'll, by prior you'll see what I mean, but first let's
Okay.
just take a very simple setting what we have been doing so far. We'll do the same. We will minimize the error between h of si and g of si. So let me just, for compactness, let me call this gi so that it looks a bit less cluttered. So we minimize this square error that we have been doing all along. So how do we do this?
So if of okay, f is a function of n parameters, right?
Correct, yes, a1 to an, yes. So we want to optimize over a1 to an, right? Again, it's the same setting where a1 to an can be any real value. So this is an unconstrained optimization case.
Unconstrained, yeah. So
So
then calculate
here,
the gradient.
yeah, so here also we'll take the gradient, right? So here what we are given is a1 to an belongs to Rn unconstrained optimization, right? So this implies FONC is gradient A, so I'll call the vector as A, f of A is 0, and let's say the candidate point is A star. This is what we are looking for. So what do we do? So this is A. So the hint is that again we have to somehow formulate these functions as some matrix vector products, because notice that I am given n samples. Okay, there are n samples and there are small n variables. Okay, let me, yeah, okay, maybe the notation is slightly bad, but I hope it's fine. Capital N is for the number of samples and the small n is for the number of variables, the AIs.
Yeah. So this is a quadratic objective, so that gives us probably some way.
Yeah, so you are right. You would expect this function to be represented as some quadratic form. You're
Yeah.
right. But we want to reach that. So how do we do that?
Maybe as a first step, we'll try to expand the sum and see how it's possible here to do.
Summation of, you
Uh,
mean this
The
particular summation?
yeah, this summation we write with component wise and see if we can simplify it from there.
Okay. So maybe I should have been clear. So these are all scalars. This is a scalar. This is a scalar.
Oh, these are all scalars, right?
Yes.
Okay.
Yes. So yeah. Sorry. These are all scalars. So x may be multivariate. That's okay. But sorry, x is also not multivariate. My bad. These are all scalars. X is a scalar. H of x is a scalar. G of x is a scalar.
Yeah, these are all scalars. Yeah.
So okay. So maybe let's look here. These are all scalars. That's fine. These h of si's. See, g of I we can't do anything. This is just some constant that's given to us. But h of si is the quantity where our variables ak's are involved, right?
Yeah.
So let's just start by looking at how to represent h of si somewhat differently. So is it easy to see that h of si can be represented as this inner product of two vectors?
Yeah. It's easy.
Right. So remember that when we say that we want a quadratic form here for this f of a1 to an, we want something like a transpose q and q a plus, I don't know, b 2 b transpose a plus d or something like that. So what we want is this vector a to appear, right? I mean,
Yeah.
I'm not saying this is some recipe. I'm just trying to say that this one way to realize that we want AIs to appear, and h of SIs give us a way to bring them into the picture.
Yeah.
Okay, so note that this is true for all I 1 to capital N. So what do? We stack these are scalars, we just stack them into a matrix. So these will be stacked, and what will end up getting is a matrix. So what we'll end up getting is h of s1, h of sn equals to 1 s. So this what you were saying, Vandermonde, this is Vandermonde matrix.
Okay. This is a Vandermonde matrix. So there will be capital N rows and small n columns, right?
Yes. So I'm just writing this down for each and every I, not doing anything else. Okay.
These things actually I read long back. Now it's slowly coming on to me. The Vandermonde matrix and all those things. Yeah.
Yeah. So here also we'll see probably not need any. We won't need to compute the determinants. Let's see. Don't know if we will need to, but so I hope that this is clear, right? So
Yeah.
what we are saying is we got. I'll just denote this compactly as saying s equals to s times a. Is it fine? I just don't want to write it long, otherwise it will be too cluttered. But if at any point if it's confusing, please let me know. Okay. So I just rewrote this as h equals to sa. So only a's are my variables. This h, this vector which I'm calling h, is a constant. This is of course a constant because these si's are given to me. This h of si is of course sorry, h of si is not constant, my bad.
Yeah, these
H
are
is a
not constant, right?
H is a function of these
Of the
variables a. So right, so
yeah.
for these n samples, the way I can write it as a linear system. That's what I should have said.
Yeah.
Okay, so right, so what do we do? So point is, we are trying to simplify this or rewrite this expression for f of a into terms which are akin to a quadratic form that we have seen in earlier problems. So having said that h is s times a, we'll just see how to rewrite our f of a. So just to recall, f of a is summation I from 1 to n, capital N, h of si minus g of I whole squared, and this is summation I h of si whole squared. I'm just doing an expansion, nothing else. So of si gi plus g squared. So any questions so far?
No.
It's okay, right?
Yeah.
So now I think you might start to see how it comes useful. So what we'll do is this summation over 1 to n is what's
this will
going to
write
come
as an
in
inner
handy.
product, right?
Yeah.
We can write it as an inner product, right? This one.
Yeah. Yes. So we'll just write it as an inner product of this with itself.
Yeah, this with itself, correct.
Right. So there's basically going to be A transpose S transpose. I mean this whole transpose the same thing.
A transpose S transpose S A. That will be the.
Yeah. So A transpose S transpose S A minus. So here also we are doing the same thing. We take an inner product of this with these quantities. So you can stack these also as a vector, right? So what I'm saying is you can call g1 to gn. Just call that as a vector. Is it fine? For each point I get some value g, or for the function g I get different values g1 to g capital N. I'll just call that vector as g. So this is nothing but the inner product of this vector h and vector g, right?
Yeah.
So I'll just write that. So 2 S transpose A transpose S transpose G and plus G transpose G. So now it's simplified by a lot. Now we can apply our FONC, first order necessary condition, and see what happens. So it's a quadratic form, and remember again this is a symmetric matrix. So we'll just get 2 times S transpose S A equals to S transpose G. Okay, so here this is for A star. So let me put A star here. A star is our candidate point, and again assuming that S transpose S is invertible here for our case, let's just for simplicity assume this. Does this look familiar?
Yeah, it's this thing. The what you call the ridge regression kind of formula, right?
Yeah. So you just do norm ax minus p squared, and if A is full column rank, this is what you get, right?
Okay. Yeah.
So I mean we are not doing that here, but you get a similar form because ultimately what we are given is we are given a bunch of samples, and it should not be surprising because we are ultimately solving this linear system of equations.
Okay. Okay. Yeah.
Right, we are finding some SA which is close to G.
Yeah. Yeah. Yeah.
Got it, right?
Yeah.
So that's
But
how.
I'm a little bit unsure. How can you correlate it with the prior information thing you were telling? A little bit.
I'll come to that. So we'll modify our objective a bit more.
Okay. Okay.
So then
Okay.
we will get slightly different results. That's all.
Okay. Okay. Okay.
Yeah. So just trying to point out that it's not so surprising that we got this result, for the simple reason that our first order condition, not first order conditions, just the way we have defined our h of x, and because we are given only some n samples, capital N samples. This is like our A, this is our X, and this is our B. Okay.
Okay. Okay.
So
Yeah.
that's why the form looks familiar.
Okay. Okay. Yeah. Got it.
So FONC gives us this candidate point. So what we'll do is we'll take a Hessian. We'll compute a Hessian for this and see what it looks like. So Hessian is simply 2S transpose S, right?
Yeah.
And the good thing is, because this form, you
Yeah.
take,
This is already.
yeah, it's all, you just take 2 times transpose X, X
This is always
transpose.
greater than equal to 0. Yeah. Yeah.
Yeah, so it will be 2 norm 6. So our second order necessary condition is also satisfied. Okay, so this is first order necessary condition gives us the candidate point, and second order necessary condition is satisfied. Okay, but can we say anything else? It would be, let's say, if I can guarantee that this norm Sx squared is greater than 0, then I can guarantee that this point is a minima, right?
Yes. Yes. Yeah. Means positive definiteness, right?
Positive definiteness, yes. Okay, so that was part A. Okay, this was part A. So let's do part B. Part B is where I was saying that we'll incorporate some prior information. So one way to maybe think about this is, let's say this S transpose S, we assumed here it to be invertible. Let's say it was not invertible. How can I make it invertible?
Yeah. You kind of, which is standard trick used in ridge regression, right? You add a diagonal entry.
Yeah,
Ridge.
you just add some constant times a identity matrix to this,
Yeah. Constant of an
so that the
identity.
whole matrix is now invertible, the resulting
Yeah.
matrix, right?
Yeah.
So yeah, I was just going to say that this is what I meant by trying out adding some prior information. It's like adding a Gaussian prior.
Yeah. This is like adding a Gaussian. I think originally ridge regression was proposed in the context of ill condition matrices, right?
I'm not sure what do you mean by that?
Means this is precisely the condition when some of the matrices are not invertible or they are badly conditioned. Then I read it somewhere or somebody taught me or something. Means I vaguely remember that fact. It was originally controlled by Hoyle and right. It was proposed for in condition matrices, if I remember everything correctly.
Yeah, I'm not sure. I'm not sure about the history about it. I just know
I think
I just know that two different problems needed to be solved. But for example, like whether you have a lot of solutions, you want to pick which one. That's where the least square solution notion came from. Started with, I guess, and then
but this is I think one of the motivation. But anyway, it's pretty old fact, right? 1960s or something.
yeah.
It was proposed. Pretty old.
Yeah, sorry, I'm not sure about the history. Maybe I'll have to read
Yeah.
up on that.
No, I just remembered it. That's what it means. A bit digression. Yeah, so
Yeah.
never mind.
Okay, so here in this case, so we already have a lot of our work cut out for us. So we know that this term will be same, will be appearing here as well. All that we have to do is we have to just have to incorporate this term, right?
Yeah, incorporate this additional terms. Yeah.
So this is nothing but A transpose S A minus 2 A transpose S transpose G plus G transpose G plus lambda A transpose A. So for the first order necessary condition, what we'll end up getting is 2 S transpose S. So the same terms as before.
Additional A will come, right?
Yeah, so and the only thing that will come is 2 lambda A.
Yeah, 2 lambda. Sorry.
So is 0, and so what we'll end up getting is A star. It's nothing but S transpose S plus lambda times I inverse S transpose G.
Yeah,
Okay.
this is the ridge minimizer. Yeah.
Yeah. So and here if you look at the uh, second order sufficient condition, it will be satisfied. Why? Because when you take X transpose S transpose S plus lambda I, so this is the Hessian. This will be nothing but norm Sx squared plus norm x squared. So
Yeah. Yeah.
obviously we are
Straight up.
doing this for x not equal to 0.
Yeah.
So
Yeah.
this is strictly greater than 0. This
So
implies
this is the positive definite, right?
positive definite.
Yeah.
So here both second order first order necessary condition and second order sufficient conditions are satisfied. So here we can say that A star is indeed the minima.
But in the previous case, we can't, right?
Yeah, so if S is invertible, so actually you can say there also. I think I maybe said just, yeah, I think this is not necessary because I think I assume that S is full rank.
But in case of an equality, we can't say that, right?
Yeah,
This
in
is
case
this
of
may
equality,
mean.
so here maybe let me just edit that. Sorry about this confusion. So here, yeah, S is full rank. And why is that? Why am I saying full rank? Because we by setting we assume that S transpose S is invertible. So the rank of this
Yeah.
is same as rank of S. Null space of
Yeah.
this is same as null space of this. So
Yes.
okay, so here it is. So here also A star is minimizer.
Yeah. Under this assumption, yeah, it holds. Yeah.
Yeah. But in general, if I am saying that okay, it's greater than equal to 0, then I cannot say anything. I can just say that okay, it is a candidate point. That's all.
Yeah. So we must be careful while doing those things a little bit.
Yeah, and this will become even more tricky when we will have constant optimization because this inner product. So right now we are doing unconstrained optimization, so we check with respect to all non-zero x. But when you do
Okay.
constraint optimization, you will have to check these x this second order condition with respect to specific directions only, specific x's. So
Okay.
that will give
Okay.
you a few more conditions that okay, maybe if such and such directions are there, only then perhaps in the constraint then it's okay. Otherwise, you still cannot say whether it's the candidate point is a minimizer or not.
Okay. Okay. So we will have to be even more careful for those cases,
Yeah,
right?
yeah.
Yeah.
So for example, for the first question will be for what directions, for what type of access should you have to check these conditions, second order conditions. That itself will be a
Mm.
theorem, an important theorem that will be
Okay.
covered later on.
Got it. Yeah.
So let's just do one more variation where I write, again we are doing curve fitting. I mean it's the same thing, but instead of the L2 regularizer that we saw earlier, lambda AI squared that we added, we will add something else. Okay, so here instead of saying that I will penalize the specific polynomial coefficients, right? I'm just talking about the average values that the function can give.
Okay.
It's
So
like a regularization in the function space, if you, maybe you can think of it like that.
okay. So H is the function that is being approximated, right?
No,
I'm
h
not.
is the function that we are having, that's the polynomial function with which we are approximating g.
Okay.
So here, see, ultimately you are putting constant on h. Now there are different ways
Yeah.
of doing it. Maybe or one way to do is you can just put a penalty on the weights directly.
Yeah.
Sorry, not the weights.
Yeah.
Sorry, the parameters, the AIs. But
Yeah.
another way to do it would be to pin, some norm of the function. So, for example, in that space, you can, because a polynomial, so one way to define inner product with itself would be this integral. So that's why I
Okay.
meant to say that
Uh,
inner product, but in that function space.
okay. I never came across this regularization before. Yeah.
So in the I mean, if you look at support vector machines, you might see representative theorem. So there you might see that you may
Okay. The representative. Okay.
you may
There it
formulate
is.
problems where you are minimizing some usual error, let's say hinge loss or squared error or whatever, and then plus you have a
Mm-hmm.
regularizer of the norm of the function in that Hilbert space, appropriate Hilbert space.
Okay. Oh. Okay. Yeah. Got it.
Right. So this will complicate things a bit here, but let's just again get used to calculating our uh, first order. I mean, just looking at first order and second order necessary conditions. So remember that this part is the same as before. We just added this lambda times integral term. So f of a will be as before, a transpose s transpose s a minus 2 a transpose s transpose g plus g transpose g plus, now here it changes, and so what will it turn out to be?
Yeah. Can you write it as a kind of this thing inner product form like here?
Okay, so let me go back here. Uh, yeah, this part. H of x is a scalar, right? So h of
Yeah.
x
H
is
of x is a
basically x transpose a.
yeah.
Okay.
S
So
transpose A.
yeah. So maybe let me remove this here. I'll just write it there itself. So h of x is x transpose a. So h of x squared is x transpose a squared, right?
Yeah.
So I'll just write it as a product of two scalars, a transpose x, x transpose a. This is nothing but a
Okay.
transpose x transpose a. This so this is a matrix, this is a vector, this is a
Yeah.
vector.
Yeah.
This
Yeah.
is still a scalar.
Yeah.
It is exactly equal to
Yeah.
h of x squared.
Okay.
So I'll just this is a standard trick we use when we are having scalars represented as these inner products, so that we can get the corresponding matrices as well in the calculation. So I'll just rewrite this as uh,
So when we have kind of these least squares objectives, always try to recast it into this form, right? With transpose and all those things, right?
yeah, in general, when you have these scalars represented as these inner products, it often helps to uh, represent it like I've done here on the bottom right, because you can
Okay.
split it into parts where one part depends on just the data and the other part depends on the
Okay.
variables. So
Okay. Yeah.
it again, it looks very similar to our quadratic forms, and it's exactly a quadratic form. So it becomes easy
Yeah.
for us to do the vector calculus.
Yeah. Okay.
Okay, so I just wrote this from here. Is it fine?
Yeah.
Okay. So maybe let me simplify a bit further, because this will this is the only complicated part here. So what we can do is we can take the integral inside, because the integral is only for the variable is x over which we are integrating, right? So we'll just write it as a transpose integral 0 to 1 xx transpose dx a.
Oh,
Okay.
you are sandwiching the integral, right, within
Yeah,
A transpose.
yeah. It's just linear terms, so I can just take the integral inside.
Yeah. Okay. Okay.
So can do a further simplification. So what I can do is a transpose 0 to 1. This is again the Van der Waal matrix minus 1. So you can just check this. You have xx transpose and you know what x looks like. So what I'm saying is, this is your x, no? X is basically all the powers of x from 0 to n minus 1.
Okay. Yeah.
So I just wrote that. So that is my x. So when you do xx
Okay.
transpose,
Okay.
you'll get a matrix.
Yeah. Okay.
Okay, so ultimately you will end up getting a very
That will
similar
be a
matrix
symmetric
that we
matrix.
saw earlier. So if we integrate this, okay,
Okay. So this is an integration of a matrix function, right?
yeah, so it will be term by term integration. It will not
It
be
will be term
something,
by term. Yeah.
yeah.
Okay. Uh,
So what will it turn out to be? Again, I'll just continue the calculation here. It will turn out to be what we saw before, which is, so maybe in hindsight I think this is what we were looking at in the earlier problem. So it is an integral of a Van der Waal matrix, that's why it looked familiar. So if you recall, this is the matrix that we had gotten
yeah.
earlier. If we started with a problem and you're discussing the diagonal dominance as sufficient condition to check
Yeah.
whether it's
Yeah.
invertible or not. So
This was for the case of
hello, your voice got cut off.
yeah. Yeah. Hello. Am I audible?
Yes.
Yeah, this was in the case of the polynomial approximation, right?
Yeah, I think so.
Yeah. Yeah. That was.
So just, yeah, I think just wanted to do a few of these to get familiar with the calculation. So this is maybe this part of how to simplify this integral may be not so obvious, but here I have shown that I can still represent it as some quadratic form. So I think I just wanted to show that. So ultimately, what will my function look like? A transpose S transpose SA minus 2 A transpose S transpose G plus G transpose G plus lambda A transpose PA. Is it fine?
Yeah,
So this is my P matrix that
yeah, yeah.
I've written here.
So and then we proceed as before, right?
Yeah, then we proceed as before.
I think it's too late for discussing the questions now.
But let's just go through as many as we can. So I think I can.
Yeah, maybe we cannot finish today because I also have to.
Yeah, so I have about 11 minutes.
Yeah, whatever we can do, we'll do.
Yeah. So just give me a second. Let me open questions.
Not instructive to go through that.
Yeah, so now let's go to the week 6 questions. So the question 1 says that I have a set of points x which satisfy this relation. Summation xi square by alpha I square less than 1, alpha I greater than 0 for all I. So the question is, does it have any extreme points? If so,
I
how many?
couldn't solve this question, as I was not sure how to proceed with it.
Okay. So let's say let's say n equals to 2.
Yeah,
What will it
okay.
look like?
Uh, kind of an ellipse or something.
Yeah, it is an ellipse, exactly. It's an
It's ellipse.
ellipse. Ellipse, but
Ah,
in the interior as well. So
okay.
there are
That I find.
uncountably many points, right?
Okay. There will be uncountable. Yeah, it's continuous, right? I mean, it's kind of curved, right? The boundary
Yeah.
because of that.
So yeah.
Okay.
So it has exactly one extreme point. Let me maybe just write the options quickly. All points of A are extreme points, and A has infinitely many extreme points. Okay, so the answer is D. Does
D,
it look
right?
like
Yeah.
right?
Okay.
Okay, so take n equals to 2 ellipse for visualization. Entire boundary is a set of extreme points.
But I think I remember the instructor was teaching during the classes that we cannot consider sets such as circle because in that case we lose the notion of a polyhedron because of this specific reason. So can we talk about extreme points in this particular case
So
for
extreme
sets
points
like
is in general for any set.
okay. It
I
need not be a polyhedral set, right?
Yeah, extreme points is just a geometric notion. Now, it makes sense that we have only finitely many. I think he is
Okay.
probably just trying to say that can we say about how many extreme points we can have.
Okay.
So in
Okay.
general, if I don't say anything, then there can be too many extreme points. In fact, that's exactly the problem with algorithms like simplex, which we will see in the
Ah,
coming lectures. So
okay.
yeah,
Okay.
it's this is a problem. So if there are too many extreme points, then how do we search through
Yeah.
such a big set, right?
Yeah, the computational complexity goes up, right?
Yeah. Okay. Question 2. So here again we are checking the number of extreme points. So we are looking at the positive orthant. All three coordinates are non-negative. X is less than 2, less than equal to 2, y is less than equal to 1, and z is less than equal to 5. So how many extreme points are there?
So this we can drawing a kind of cube, right? Enclosing region and then in
Yes, correct. So it's a cuboid.
cuboid, yeah, sorry.
So this implies 8
8
extreme
extreme
points.
points.
Okay. So which of the following, next question is, which is a feasible region of linear programming problem? So the first one says that norm of x squared is less than equal to 3. Okay. Second one says that the modulus, I mean each quantity is greater than equal to 1, modulus of that. Then third case is the inequality flipped, so mod x less than equal to 1, and there's another one where you can say x transpose x greater than equal to 1. All such directions x such that x transpose x greater than equal to 1, and A is a positive definite matrix. So how do we do this?
So constraint should be linear, right, in a LP,
Yes.
and it should be bounded, right?
It doesn't have to be, right?
Okay.
So in general, so very crudely, what do we have? Ax less than equal to b, right? Where we just modify it to say x equals to b and x greater than equal to 0. But
Okay.
beyond
Okay.
this, we cannot say anything.
So looks like B and C can be correct, right, from the
Which
first
ones?
approximation. B and C can both be correct by these conditions because they are both linear, the constraints.
Uh, the constraint in D is not linear, right?
No, I am saying B and C.
Oh, okay, okay. So, okay, sorry. So let me just. So this is not right. This is not true.
This is not right, yeah.
Not linear.
The same for the first one also.
Okay. First one. Yeah. Okay. Okay. Then.
Yeah, then C can obviously be a solution. That's sure because you can write it as a linear inequality in the standard form.
Yeah. So this, because this is not convex and this is the only convex.
These are convex.
So let me use
So B is
green.
a disconnected set, right? Yeah,
Yeah. So you can just imagine in the 1D case.
yeah, yeah.
So it's this and this, right? So we'll do a few more before we close. It's fine.
Yeah, we
Squeeze.
do probably two more. Okay.
Yeah. Okay.
Yeah.
So we are at 2. Let's just do 2 more. Oh, we did 3 actually. 4.
Yeah, we'll finish at five.
Yeah.
Five problems. Yeah.
So there are 2 linear programs. One is saying you maximize over x, c transpose x, ax equals to b, x greater than equal to 0, and there is another problem which is saying minimize x, t transpose x, ax as b, and x greater than equal to 0. Constraint is same, but
Yeah. So
work
the
is,
yeah,
yeah.
feasible regions are the same, right?
Feasible regions are the same, yes. So okay, let me write this. Basic feasible solution of both are same. Is this true or not?
Yeah, this is same, right?
Why is that?
No, the matrix A is the same for both these things, right?
Yes, yeah, correct. So BFS is an extreme point. It only depends on the feasible region, right? It
Yeah.
just depends on
Yeah.
this ax equals b, x greater than equal to 0,
Yes. Yes.
which is the same.
Yeah, but the objective cost function may be different, but
Yeah,
the solutions are the same. Yeah.
yes, for both the LPs. Okay, last one for today. Consider the dual constructed from the primal LP. Okay, so there is a primal LP. Okay, maybe let me just denote it briefly by P to avoid clutter. So there is a primal problem which is maximize C transpose X, AX as P, X greater than equal to 0. Which of the following are false? Okay, so option A is objective function changed from maximization in primal to minimization in dual. Is this
This
true?
is true, right?
Yeah, because it's just the way we have formulated the problem, right? If we have a min, it
Yeah.
just max, I can write as a min of minus
Yeah.
min
Yeah.
of minus C transpose X. Right, so it's just taking care of the negative signs. So basically,
Yeah.
if you have a max here, it gets converted to a min correspondingly, right? So this is fine. This is true. What's the next option? Let's see. Each column of matrix A in the primal corresponds to a constraint in the dual.
That is also true, right?
Why is that?
Because the dual is formulated as a transpose kind of constraint, right?
Right.
So that means each column get transformed into rows in the dual constraint, right?
Yes. Yes. You are right. Okay. The number of primal variables equal to number of dual constraints. Is this true?
Mm. Variables means n cross n, so there should be n variables for the prime, and for the dual you have cross n cross m. So yeah, that is true, right?
Yeah, that's
That is
correct. So
true.
just
Yeah.
by looking at the form here in the dual case, the constraint will be A transpose Y equals to B. What is that constraint?
Let's
A transpose Y less than equal to B.
yeah, less than equal to B.
So just by looking at the primal dual form, we can see that the number of primal variables is exactly the same as the number of constraints in the dual problem, right? So there is no relationship between objective function values of the primal and dual. What about this?
This is false, right?
And the reason is,
No relation between the objective of, yeah, because one is greater than the this thing of the other, right?
yeah, we have
A strict
seen proof of weak duality.
weak duality.
Okay. So
I think
yeah,
we'll leave it at that for
yeah. So
today.
I can cover the remaining ones next time, and I'll continue to solve few more problems. So I think maybe that's going to give a better
Yeah,
point.
especially today's thing was very instructive. It was illuminative and instructive for me. Okay, at least for me.
Yeah, sure. Yeah, just keep sharing the feedback so that I can keep working on the format. So as
Solve
of
some
now,
problem.
I've decided to continue to solve some more problems.
Yeah, and
Um,
I'm also solving some void problem. So maybe if I'm in doubt, I can share it with you. Okay.
yeah, please do. Yeah, if you have any doubts, please ask me. So just one second, let me stop the recording.